All right, so our next advanced theory of bonding is known as molecular orbital theory, or MOT. This one kind of describes quote unquote real bonding. So this is the most advanced way to do this. And really, you need some kind of like supercomputer, right? Some strong computational power for all, but super simple molecules. Remember that all of kind of chemistry and all of chemical bonding is the interaction between the nucleus, electrons, and then other electrons. So what computational methods try to do is take these interactions into account and try to find some kind of minima, some kind of low energy state where they're most likely going to be at. And that's very, very complicated because there's a lot of interactions, and then two, these subatomic particles behave very weirdly. Molecular orbital theory is very similar to valence bond theory in terms of its hybridization. So it's kind of like hybridization. The orbitals are mixing. So atomic orbitals are mixing in order to become molecular orbitals. Hence molecular orbital theory. So the main difference between valence bond theory and molecular orbital theory is that in molecular orbital theory, the molecular orbitals, as the name would imply, belong to the entire molecule. So chemical bonds are no longer between two atoms, but they compromise the entire molecule. So remember, this all comes back from the kind of the idea that electrons are wave-like. And so they can interfere constructively or destructively. And so what happens is you have atoms combined. So here's the hydrogen with its 1s orbital and 1 electron each. And then these are the atomic orbitals, or the AOs. And then in the middle, they combine to form these molecular orbitals. When they combine constructively, they form a lower energy state. And when they combine destructively, they form a higher energy state. So down here would represent our sigma bond. And then up here, called sigma star. The sigma orbital is what's known as a bonding orbital. And then anything with this little asterisk, this star, is an anti-bonding orbital. Since hydrogen has 2 electrons, we go ahead and fill in that center molecular orbital. Since H2 has each hydrogen has 1 electron each for a total of 2. We fill the 2 electrons, same as we would with our electron diagrams. And so both of the electrons are going to end up in this lower energy state. From these molecular orbital diagrams, we can calculate a lot of things. One thing that we can do easily by hand is calculate the bonding order. The bonding order is the electrons in the bonding orbitals minus electrons in the anti-bonding orbitals. Divide by 2, because there's 2 electrons in a bond, and then that gives you your answer. For example, our hydrogen one, we have both of these in a bonding orbital, none of them in an anti-bonding orbital. Divide by 2, you get 1. The bond order is 1, and that makes sense from our Lewis structures, right? This hydrogen has a single bond. If you try to do that for the same element up next, helium, it has its 1s orbital filled. And so we're going to try to make here He2. This is sigma, this is sigma star. We fill it up, we have 4 total electrons, 1, 2, 3, 4. And then when we go to calculate our bonding order, we have 2 in the bonding orbitals minus 2 in the anti-bonding orbitals, divided by 2, you get 0. And so since the bonding is 0, that means that this molecule does not bond to each other. And so H2 doesn't exist. And then here's just kind of a picture of a slightly more complex situation, but not really too much more complex. On the left is the same diagrams we've been drawing. Just now down here is the 1s orbitals. You can see when they mix constructively, we get one color, right? These are the waves mixing constructively. And then over here, you get deconstructive interference. And then the same thing happens for the 2s orbitals, and then the p orbitals go ahead and combine. What you can see is that in all of these cases, the electrons belong to the entire molecule, not just one atom. And then on the right is just a slightly more complex situation with a slightly larger molecule. These are just examples of some molecular orbitals. Don't worry about the rest of the picture. All I want you to notice is that the electrons are spread out through this entire molecule and not just one bond, right? So molecular orbital theory takes the next step and says, hey, these electrons aren't localized in one area. They're actually all throughout the entire molecule. Anyway, so what do you need to be able to do in terms of molecular orbital theory? I'm not going to ask you too much about this. I just want you to be able to fill in an MO diagram and predict bonding order, as well as one more thing, which we'll see in the next video. So for example, you might be given this blank MO diagram, asked to fill it in for, let's say, O2, and then predict the bonding order. Well, if we think about O2, each oxygen has 6 valence electrons for a total of 12 electrons. You can ignore the left and the right side. Those are the atomic orbitals. We're really just interested in the center here, the molecular orbitals. And so then we just start filling them in accordance to the Pauli exclusion principle, right? So 1, 2, 3, 4, 5, 6, 7, 8. They're degenerate, so they get 1 each first. 9, 10, 11, 12. Cool. So we've got everything filled in. Now we want to go ahead, collect or calculate our bonding order. And so what we're going to do is we're going to count things in the bonding orbitals. So these 2 down here in a bonding orbital, and then these 6 are over here in a bonding orbital. So we've got 8 electrons in bonding orbitals, and then you want to count the ones in non-bonding. You see that little star there? That tells you that it's a non-bond or it's an anti-bonding orbital. And then you see that star next to that P as well. That tells you that it's an anti-bonding orbital. So we've got 4 electrons there. 8 minus 4 divided by 2 is 2. And that accurately describes our bonding in O2, right? Our Lewis structure matches the molecular orbital theory. Note that the bonding types also match. In this kind, we should expect to have 1 sigma bond and then 1 pi bond. We can see that these 2 cancel one another out. These 2 electrons signify our sigma bond. You see it's an S for sigma. And then over here, this signifies our single pi bond, right? This P for pi. And then we have the bonding and the anti-bonding, which leaves a net of 1 pi bond.